Hello, welcome to all. Welcome to lecture number 6. Lecture number 6. So in this lecture we will cover an alternating series and an important theorem of calculus, that is Leibniz theorem. Alternating series and Leibniz test. Here we will say theorem because we will actually prove the theorem here. So let's define what is alternating series. So alternating series is a series alternating series is series whose terms are alternately positive and negative. See, let's have a quick example. So example number 1, 1 minus 2 plus 3 minus 4 plus ... which is same as sigma minus 1 is to n plus 1 into n, where n goes from 1 to infinity. So if you replace n is equal to 1, you will get the first term plus 1. If you replace n is equal to 2, you will get minus 2, so on and so forth. Second example, 1 minus 1 by 2 plus 1 by 3 minus 1 by 4 plus ... which is same as summation minus 1 raised to n plus 1 upon n. Again my n goes from 1 to infinity. If you elaborate this, you will get the required the LHS. There's one more example, third example, minus 2 plus 2 square minus 2 cube plus 2 cube plus ... which is same as summation minus 1 raised to n, 2 raised to n, and n will run from 1 to infinity. Right. So we got an idea of alternate series. The only one thing one should remember, when you get an alternately positive negative, then it becomes an alternating series. Now let's state what the result, which is our target of today's lecture, that is Leibniz theorem. The theorem, the statement is as follows. The series sigma minus 1 raised to n plus 1 an, n goes from 1 to infinity, converges if following conditions are satisfied. So The series is convergent if the following conditions are true. So what are the condition? Condition number 1, the ANs are all positives. Number 2, the nth term, the an is always greater than or equal to an plus 1 for all n belongs to natural number. This means that the sequence an is monotonic decreasing sequence. And third, the nth term should goes to 0. If my an satisfies these three conditions, then we can straight away say that the alternating series is convergent. We will prove this. The proof is it is a typical proof that we will form a sequence of partial sum, and we will show that both the sequence of partial sum we will show that the sequence of partial sum is convergent, hence the series is convergent. But taking say a sequence of partial sum, what I will be doing, I will take the sequence of even partial sum, sequence of odd partial sums, and I will show that both sequences are convergent. If the sequence of odd partial sums and even partial sums are convergent, then we can say that the sequence itself is convergent, and that would imply that my series is convergent. So let's prove the theorem. So proof. Firstly, we consider the even partial sums. So even partial sum means we should start with S2. So S2 is equal to A1 minus A2. Now since an is always greater than or equal to an plus 1, so a1 is always greater than or equal to a2, so a1 minus a2 is greater than or equal to 0. The reason of this is it is mentioned in a given condition number 2 that an is always greater than or equal to an plus 1. So that result we are using. So since an is always greater than or equal to, this is since an plus 1 for all n. Now since I'm talking about the sequence of even partial sum, after S2 we will have S4. So S4 is equal to A1 minus A2 plus A3 minus A4, which is same as, this is basically your S2, and this is A3 minus A4. Now again I'm writing this in bracket, so you could see that this bracket is always greater than or equal to 0, right? So this S2 plus that positive term is always greater than or equal to S2. So what I got is S4 is greater than or equal to S2. Similarly, one can see that S6, which is same as A1 minus A2 plus A3 minus A4 plus A5 minus A6. But this first 4 terms will contribute to S4, and this last 2 terms A5 minus A6. Again, this A5 minus A6 is greater than or equal to 0 because of this an is greater than or equal to an plus 1 for all n belongs to natural number. So this is definitely greater than or equal to S4. So S6 is greater than or equal to S4. If I continue in this manner, I will have S of 2n is same as S of 2n minus 2 plus a of 2n minus 1 plus, sorry, it should be minus now, minus a of minus a of 2n. Now this bracket is positive, so this implies that this is greater than equal to s of 2n minus 2. So you will observe that we got a sequence uh, where S2 is smaller than S4, S4 is smaller than S6, S6 is smaller than S8, S8 is smaller than S10, so on and so forth. At last, Sn of 2n minus 2 is smaller than S of 2n. So the sequence is as follows: S of 2 is less than equal to S of 4, so which is less than equal to S of 6, which is less than equal to S of 8, dot dot dot, less than equal to S of 2n. So we will observe that the subsequence, this is basically a subsequence, S of 2n is a monotonic increasing sequence. So this would imply the sequence S of 2n is monotonic increasing sequence. This monotonic increasing, and if I could prove that it is also bounded above, then by monotonic increasing theorem we can straight away say that S of 2n is convergent sequence. So now I need to find out a upper bound for the sequence. If I could get a upper bound, then I will say that it is bounded above. Also, S of 2n is same as a1 minus a2 plus a3 minus a4. At last we will have a of 2n, so it is same as minus a of 2n minus 2 plus a of 2n minus 1 minus a of 2n. Right. So which is same as, so if I take a minus sign common from this, I'll have a2 minus a3. Similar, this is same as a, here I'll get a4 minus a5. Similarly, I will have a6 minus a7 dot 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 minus a of 2n minus 2 minus a of 2n minus 1 minus a of 2n. Now, since that given condition is an is always greater than equal to an plus 1, so this would imply this each and every bracket is positive. Each and every term is positive. Also, it is given that all an's are positive, so a of 2n is also positive. So a1 minus, you are subtracting positive terms, so this would definitely imply that this is less than equal to a1. So this would imply S of 2n is always less than equal to a1. This would imply S of the sequence S of 2n is bounded above by a real number a1, positive real number. So the sequence S of 2n is monotonic increasing as well as it is bounded above. So by monotonic increasing theorem, which we have studied in the first year BSc, semester 1, the sequence S of 2n is convergent, and we will say converges to S, that is limit as n goes to infinity S of 2n is equal to S. So let's call this as one number. Let me call it an equation A. Now on the similar line we will have the sequence of odd partial sums. Now consider the sequence of odd partial sums, that is S of 2n plus 1, which is same as S of 2n plus A of 2n plus 1. If I apply limit on both sides, then limit of n goes to infinity of S of 2n plus 1 is same as limit as n goes to infinity S of 2n plus limit of n goes to infinity A of 2n plus 1, which is same as this limit. We know this limit is nothing but S by our equation A. We have said here this is S. And what is this limit? At the very starting we have said in theorem that, if you remember, let me check out the statement. Your an goes to 0. When you say an goes to 0, that means for any n, this would imply that limit of a of 2n plus 1 is also goes to 0. So this limit is straight away 0. So what I got is the sequence S of 2n plus 1, that is odd term, also goes to 0. So sequence of odd partial sum goes to 0, sequence of even partial sums goes to 0. This would imply the sequence S of I should rectify my mistakes, I'm sorry. This implies that S of 2n plus 1 goes to S, not a 0, that goes to S. So now this would imply the sequence S of n is convergent. Now it could be a small exercise. One could see that if you get two subsequences where one is the sequence of odd partial sums and the other one is the sequence of even partial sums, and if both converges to same limit, then we can straight away say that the sequence is convergent, the parent sequence is convergent. That could be proved easily, one can think of. So if Sn converges, this would imply series -1 raised to n plus 1 an is convergent. This completes the Leibniz test. So in lecture number 7, we will study the problems related to Leibniz test and absolute convergence, conditional convergence, and normal convergence problems using the Leibniz test. Thank you.